What we'll do today is we'll move to the last chapter of module 2. I know module 2 has been very big and it is the largest module, and scope was also most of the questions, half of the question will come from module 2 only. So it had to take more time. I don't think other modules will take so much of time. So this is the last chapter of module 2, which is on the generative AI. Now I know a lot is evolving and changing in the field of generative AI, but I will still stick to the syllabus that GARP has mentioned as of 2025. Okay, so as even today, the exams that are going to be held in the middle of 2025 and mostly end of 2025, the syllabus is going to be similar to what I'm going to navigate in the next 1 hour. But it is quite obvious that this particular chapter will change over the course of time, and because this is such a evolving field, that is the reason that all the risk management etc needs to be done, especially in the case of generative AI. Okay, so what is generative AI? One of the layman definitions of generative AI is that if it is some kind of a machine generated content, it qualifies to be generative AI. Now this content can be text, this content can be image, this content can be audio, and this content can be mix of images and audio, which is videos. So your output can be a combination of all of these things, and I mean, if we look at all the models that have come up in the last 2 years, the quality of the generated content has become very human like. There has been a lot of trends in the recent past, like Gibby arts and images, deepfake videos, audios, etc. So there is a lot of debate happening now whether we should give some kind of a credit to the original inventors of some of these arts, etc. But let's keep that aside. So this is some of the content that can be generated using the power of generative AI. Now if we look at the how side of things, how do machines generate all these different kinds of contents, then let's talk about, say, text, images, and then we'll talk about other things also as we move forward. So and when it all started, we start calling it LLMs because, and this L stands for language, which means that it is a text. And now that we have the new large models which are more multimodal, we call them as large multimodal generation, etc, or large multimodal models. So LLMs, and how do they generate content is there is something called as a transformer. We'll briefly talk about what a transformer architecture is, but we'll not get into too much of details of what a transformer model is, because it is quite complex and I don't think it is needed for passing this exam. Then there are models like stable diffusion, which is also kind of a neural network, but this is more to do so with image generation. Then there are variable auto encoders, which are also used for image generation. We don't need to get into a lot of details, but you should know that these are the models that are used for generation of images. Okay, there is something called as GAN, which is generative adversarial networks. Okay, so what happens in case of GANs is there are two neural networks. One is called a generator, and the other component is called as a discriminator, or uh, which identifies if whatever is created by generator is good or a bad thing. So let's suppose you want to generate the images of dogs. So initially, generator is going to give you some kind of images, and the generator is going to tell whether it is a right image or a wrong image, whether it really represents a dog or not a dog. So iteratively your generator will become so good that the discriminator will not it will not come to know whether it is a real image, or it is a generated image. So that's how GANs work. And then there are this GARP also talks about RNNs, recurrent neural networks, which we spoke earlier in the day. Not exactly a part of generative AI, and with the advent of transformers there is a very less use of RNNs, but since this is there in the syllabus we can talk about it. So what happens in recurrent neural network is that, especially for use cases where there is a stream of inputs, or there is some kind of a stream, or a kind of a input where with every passing time you get new data, like even text data can be a stream data, audio data can be stream data. So in that case what happens, that if you are at a time t, your whatever is your output from your time t minus 1, that goes into your hidden layers of time t, and it keeps moving. Since this is more sequential in nature, it is more time consuming, compute consuming. So not after the advent of transformers, it is not so popular, but still it is a part of your syllabus. So that's how recurrent neural networks are also come into picture. So these are some of your models that are used in case of generative AI. Now let's get into the next reading, which is about word embeddings. Now we spoke about word embeddings in the last chapter of natural language processing. What actually happens is that see, whenever there is any kind of text, the text needs to be converted to some form of a numeric input so that it can be consumed by algorithms, whether it is a neural network or some kind of a old school machine learning algorithm, because text as such directly cannot be understood by a computer. While there are some researches happening these days where they are saying why can't more like a linguistic kind of a approach where text directly can also be interpreted, mostly semantically, syntactic analysis, etc., etc. But let's not get there. Most of the text needs to be put into a numerical form or some kind of a vectorized form, and then this needs to be converted to an algorithm. So this part, text to numeric form, this is called as word embeddings. Now word embeddings have seen a lot of evolution. There are popular libraries like word2vec, globe, fasttext, etc., which can do this text to numeric representation. There are static embeddings, and then there are more contextual embeddings. When I say static embeddings, it means that for a word W, if there is a vector V, it is static. The bank will have some kind of a numerical representation, and whenever I do a conversion of a bank to the numerical representation of a bank, it will be same, or context, there is no context to it. In contextual embedding like your BERT, etc., your context is also put into perspective. So the way a word comes into a sentence or a particular context, your word W can have different representations depending upon the context. Okay, so we will talk more about static embeddings, because that's what is spoken in GARP. So there are two methods to do it. There are mainly two methods to do it, and those two methods are also kind of related to each other. Okay, one is called as CBOW and the other is called as skipgram. So what happens in CBOW, and these are like your mirror images of each other. So what happens in case of CBOW or continuous bag of words is that if there is and you can call it as by token or you can call it a word. So if there is a word at ith place, and then there are some words which are preceding this, and there are going to be some words that are going to be after this, etc., etc. So now if I mask this word, or if I eliminate this word, then if I try to find out the probability of word wi, knowing what is preceding and what is exceeding these words, that's called as continuous bag of words. So in this case, what happens, I take all these wi minus k to wi minus 1, then wi plus 1 to wi plus k, depends upon how many preceding and exceeding words you want to take, and based on that we find out wi. So this is called continuous bag of words. And if we do the opposite, if based on wi, if I try to find out wi minus k till wi minus 1 till wi plus k, so if I do the opposite, it is called as skipgram. So if you go to any of these libraries like your word2vec or fast text or anything that can give you these things, then it will have parameters for both CBOW and skipgram, and generally it is seen that both these scenarios will give you similar results. So these are the two architectures. There can be questions related to this, that what happens in case of CBOW, what happens in case of skipgram. See, once you do a numerical representation of a word, you can do some numerical operations on some of these words, and surprisingly or intuitively, you will be surprised that some of your basic mathematical computations can give you very, very good results. Okay, for example, if you do, let's suppose, a vector representation for India, and let's suppose you subtract the vector representation for Pune, where I am present, and then probably you add the vector representation of Bangalore, you may get the vector representation of Karnataka. Okay, so those kinds of things are there, or there can be more things like, if there is a vector representation vector of, say, man plus a vector of, say, rich and vector of, say, royalty, it may be same as the vector of king, and if you subtract say vector of man from this, and then you add the vector of woman, it will be vector of queen. Okay, so what happens once you do a numerical representation of all these words, you can play around with some of these semantic elements, and you can get the vector representation of say a female gender or those kinds of things. So that's how it works. So that's on the vectorization of text to vectors. And most of the times, when it all started, these vector representations used to be 1 into 300, then it became 1024, and now there are even larger vector representation like 4096 or even bigger than that. So the higher is the vector representation, the more granular it becomes. But since you need to consume billions and billions of tokens, so as you increase your vector length, your compute will also increase. Okay, so next small reading is on RNN. Will not get into too much of details because I think in the introductory scheme of things we have already spoken about RNNs, where what we are saying is that if it is t equal to 0, this is a kind of a neural network, and there is some input to it, and then there is an output to it. Then at t equal to 1, and let's suppose there is a wi here, and then you have wi plus 1, which is also getting into a neural network. So in addition to that direct input of whatever is your numerical representation of a word, you also input whatever comes out of your n-1 layer. Okay, and it keeps happening. So that this is why it is called as recurrent neural network. And then there were some variants of recurrent neural network as well, like GRU or LSTM, etc., etc. And those LSTM kind of models were very, very popular till transformer actually came into picture and became so good that everybody forgot about LSTM. The problem with RNNs is that you can only come to this place once you are done with this place. Okay, you cannot achieve a lot of parallelism, and that is the reason that RNNs are not so widely used these days as they used to be, and so next we will talk about a little bit about the transformer architecture. Now, in around 2017, if I'm not wrong, there was a person called as Vaswani, and there is a very, very famous paper which says attention is all you need. So that was a paper which introduced the architecture of transformer, and it says that a transformer is a combination of two things. One is an encoder and the other one is a decoder. Okay, so it is a kind of a sequence to sequence. There is input and it encodes it into some kind of an intermediary format, and then there is a decoder which is going to give you the output. And then within, if you look at this paper, you don't have to look at this paper, but if you get into the detail of things, then this encoder itself is a combination of positional encodings and a lot of other things, and then that goes into a decoder, and then there are value pairs and value vectors and other kind of vectors, and there is a lot of computation that happens in the decoder which results in the final output. And there is a lot of math that goes inside encoder and decoder. I can create a separate video of getting into the details of encoder and decoder if you are interested, but for the purpose of GARP exam, you don't have to get into so much of details. I'll just tell you the intuition of some of these things which are a must-have for passing the exam. So yeah, transformers have encoders as well as decoders, but then there are variants of transformers which are like encoder only, and then there are variants which are decoder only, and then there are variants which are which have both. So encoder only transformer means that it is input till this place, and decoder only means that it is only going to do the decoding. So all your contextualized embedding kind of models like your BERT are your encoder only transformers, and all your models like your GPT, etc., are decoder only transformers, and all your models like your Google Translate is both sequence to sequence, so it has an encoder and it has a decoder. Now most of your LLMs are decoder only transformers because they generate, right? So they get a prompt, and using the prompt it is like finding the next token and then the next token, etc., till they encounter the end of the paragraph or end of the sequence, etc. So there can be questions regarding this intuition, and then there are other models. There are also models which have more than one encoder or more than one decoder, etc., but I'm not going to get into those details for the purpose. But you let me know in comments if you want to know in lot of depth. We can talk about transformers for 2-3 hours if needed, and it is very, very interesting because it is kind of a breakthrough in language processing. And so there are two kinds of opinions. One opinion is that it has killed all the linguistic NLP discussions. So if I have to discuss about the Paninian linguistic analysis or some other form of empirical linguistics, so all of that is not taken into consideration so much these days, because by building this kind of a decoder only transformer, which is like trillions of parameters being trained on so much everything that is available on the internet, so it has found patterns of information and it is giving state of the art results. But the models are big, you cannot host them locally, it needs to be on the cloud, and there are only few providers that are doing all of this. It's actually not distributing or democratizing NLP to more and more people. If we go to the traditional NLP methods, or more on the linguistic NLP methods, where we used to do some kind of a syntactic and semantic analysis, and then find out patterns of information and things like that, it was more smaller models, it was more explainable and linguistically curated, easy to understand, specific to a language, etc. And with more than 7,000 languages in the world, we may not be able to create LLMs for all of those languages, and some of the remote languages may not have that kind of a supporting ecosystem. But anyway, let's park that discussion for some other time. Let's do the next thing, which is on the next reading is about the cloud-based LLMs, which is what I was trying to tell you. Most of the LLMs are anyway on the cloud itself, because and it's a evolving field. So just a couple of days back there was Llama 4, and then there is before Llama 4 came into existence, there is this DeepSeek which came, and then of course there are GPT models, etc. Okay. Your GARB, the content was published sometimes before the advent of DeepSeek and Llama 4, so so it may not have so much of information, but these LLMs are mostly prescribed into two parts, which are more proprietary models, okay, and which are like open source models. And open source is also more like Llama 4, where you have all the training data and all your code as well available, so that if you want, you can recreate this entire thing from scratch. DeepSeek is also open source, but it may not have so much of information how the foundation model was trained, what kind of data it was used to train this in the first place. And that's where there is a lot of debate whether it is a kind of some kind of a distilled model from GPT, etc., or have they done it from the scratch. And then there are more proprietary models like GPT, which are proprietary. You need to pay some money to get it, and it is a kind of a, as of today, if you talk the performance of open source and proprietary models are almost at par. And then there are more domain specific models, not too many, but there are more domain specific models, like your Bloomberg came up with Bloomberg GPT, which is related to finance data. And then there are more domain specific models which are for a particular domain or for a particular piece of information. So and this is also proprietary. You cannot recreate this, of course, because Bloomberg has trained this on their data, and that's the key monetization thing for them. So they don't want to share this with everybody just free of cost. So this is how cloud-based LLMs are there. So that's the next reading. Then it talks about applications, and that's it. Okay, so now the next reading is about prompt engineering, small reading. So what happens that if you have an LLM, which is nothing but a transformer model, you need to ask a question. It's a kind of a Q&A, and then you get a response. Now anything that can be formulated into a natural language, and you don't have to become very abstract and open-ended, because if you are abstract and open-ended, you will not get a good response. So there are best practices and there are strategies to form the query, which is called as prompt engineering. So in fact, this was kind of a go-to skill a couple of years back, maybe 1 year back, when we used to need good prompt engineers who can formulate the question in the right phrase and right language. And what happens in prompt engineering is there is a question, there is a context that you need to give, that okay, this is a context of creating a recipe, and it is a recipe to be created for kind of an Indian setting. Most of the people in India, they like spices, and there is a lot of people in India who are vegetarians, and so that's where you give all the context, and then you ask a question that can you give me how can I create a kind of a soup that somebody can drink when somebody is not well, or stomach is upset, and then you can give some kind of constraints, etc. So there is a prompt template that we create, and then your questions can vary, but if you are asking all these questions in the same context or in the same business process, the rest of the things can remain consistent. Okay, so that's where prompt engineering comes into picture, where you create a prompt template, and then you create some, and you keep redesigning it, and if it is not an English language, if it is some other language, then also you have to experiment, try and again and see what kind of, if your LLM is multimodal or multilingual, what kind of constraints or context you need to put so that to make sure that your response is more accurate. Okay, so there are three things that you generally look out in the response. One is, of course, the accuracy, which means that your hallucination or misinformation needs to be minimized. One is the volatility, and one is your the bounded truthfulness. Okay, not used, these terms are not used in GARP, but I'm just telling you from my perspective that your output needs to be accurate. There is no rocket science about it, that it needs to be accurate. The people talk about hallucinations. Hallucinations is misinformation that is present in your raw data, or the data that is consumed to create these LLMs. So if just to give an hypothetical example, if 2 plus 2 is 5, and that's how it sees in your data, then it will give you 2 plus 2 equal to 5. because it is not actually doing the computation, but it is only finding the next token. And if 60 out of 100 times you see 2 plus 2 equal to 5 in your raw data, which is used to train your LLM, it is going to give you that kind of an information. So that's the hallucination or misinformation. So that needs to be that needs to be controlled. The second is the volatility, because your LLMs are more creative in nature, more non-deterministic in nature. So every time you pass a prompt P through an LLM, you will not get the same response R. Okay, so you will get R1, sometimes you'll get R2, sometimes you'll get R3, and so on. So since there is a lot of non-deterministic behavior in your LLM, you have an ability to control how much creative you want the LLM to go. And one of the parameters that you set for this is temperature. So whenever you are using an LLM, and every LLM can have a different range of values, but I think mostly it is between 0 to 2. So if you set the temperature as 0, it becomes very non-creative, and the output is also not going to be great. It is mostly going to be more like a semantic extraction, more like your earlier erstwhile information extraction system. But if you set it as 2, it becomes highly creative, and it will try to generate more and more factual, fictional information. So it depends upon where you want to land between 0 to 2, and that's how you are going to decide on the volatility of your output. And then bounded truthfulness is something that is more applicable to some of your architectures like RAG, retrieval augmented generation, where you want your output or responses to only come from your prescribed knowledge store. Okay, so you don't want it to extract anything from the rest of the internet, but you want it only to get all the information from the prescribed knowledge store. So that's how you measure when you try to use generative AI to do some of the use cases of information extraction, especially in an enterprise environment where you don't want to go to the outside world to reduce misinformation or hallucination. Then you have means and measures and matrices to find out if your output is is bounded well with respect to only getting it from the knowledge store and not going to the internet. So that's the reading on the general stuff around LLM use and things like that, and temperature and prompt engineering and prompt templates. And then there is a small reading on the use cases, or where can generative AI be used. And again, it can be used for retrieval, which is information extraction, or extraction of information, or it can be used for generation, which is the generation of new content, whether it is text based or images or audio or video, etc. So when it comes to retrieval, it can there are use cases like your Q&A, or we can also say that it is some kind of conversational business intelligence. Okay, so there are a lot of there used to be a lot of reports and dashboards that a lot of company senior people used to look at. So now instead of looking at dashboards, you can just put a question and say that I need the sales data for last month, and it is going to create a dashboard on the fly and tell you that this is how the sales data for the last month looks like. And you can say, okay, now I want to compare this with the last year's same quarter. So there can be conversational BI, there can be more chatbots kind of stuff, which is also retrieval and some kind of a generation also. And then there can be emails or marketing content that can be generated. Marketing content, like if if Coca-Cola wants to do an ad campaign for India, uh, and it has some kind of a image that it has already set up in Singapore, which has some kind of a background of Singaporean landscape or Singaporean architecture, and there are few people in the background which are also drinking Coca-Cola, and it says that change the background to something or make it more contextual for Indian setting, so it can change the background to Taj Mahal and change the skin tone of people, men and women and kids that are there. So that kind of a generation things are also there, and then there are more advanced use cases that can have speech and those kinds of things. So things like your call centers can get entirely eliminated if you can just go and talk to a agent, a robotic agent who can conversate with you, who can get you all the information and solve all your problems to be. So those are some of the use cases around generative AI, which brings us to the end of this chapter. And now we'll start with module 3 uh, from next lecture onwards, and you can have a reading of this chapter on your own as well. And I'm sure in the times to come GARP is going to revise this chapter a lot, because a lot is changing. But let's meet in the next lecture, which is going to be on the risk and risk factors. Thank you.